Hello, welcome back to day 7. Wait. Oh, nice. I've been doing this for a week now. W consistency. Oh no, it's a hard problem. K's smallest amount of single denomination combination. You're given an integer. An infinite number of coins. However, you are not allowed to combine coins of different denominations. Return the kth smallest amount that can be made using these coins. So k equals 3. So coin 3 can be 3, 6, and 9. Okay, I see what it's doing here. Okay, so first thing that I think of is binary search, right? So, for example, if I somehow manage to get this list, right? So let's say these are the numbers, and I need to find the kth number. So instead of iterating, I can just binary search this number. So I can binary search in a range. Let me see. So k is up to 2 to 10 to the power of 9 times 2. So I will binary search in a range of 0 to 2 to the power 2 times 10 to the power of 9. And then I ask the question, how many possible, what do you call this? How many amounts? Hold on, I'm so bad at writing with my mouse. Less than or equal to, let's say I'm binary searching for x. Okay, it has to be less than or equal to x. Okay, so now I just need to find a way to do this efficiently. So my goal here is to find an x that when asked this question, it will return k. And I want to find the smallest x such that asking this question returns k. Okay, so how do I answer this? How many possible values are there less than a number x? So for each of these, I can just I can use inclusion exclusion. Okay. So I will need to make a helper function. Let's call this count value for a number x. To be honest, if k is 2 to the power 2 times 10 to the power of 9, this number that we're looking for could be a lot higher. So it's 25. Okay, so it's going to be 25 times this, which would bring our largest possible value up to, let's see, so 25 times this, that's going to be about 4.5. No, it's going to be 5 to the power of 5 times 10 to the power of 10. Okay, so this will be our upper bound, which means we might need to use long here. Actually, I'm just going to use long everywhere. Okay, so now how do I count this? Coin's length. Okay, so this is just something I know. I'm going to try to explain this. Alright, so let's say you have denominators 2 and 3, right? And you want to count because this is basically asking how many numbers less than or equal to x is divisible by at least, and I have to string this. This is important. At least one value from the given numbers, like 369. Yeah. So how do I count? Let's say 2 and 3. I want to count how many numbers less than x that is divisible by at least one of these two numbers. So first, let's ask a smaller question. How do I know how many numbers are divisible by 2? Well, that's easy. I just take floor of 2 over x over 2. That's it. And 3 is floor of x over 3. But then, what about, I cannot just add this, because you can imagine as a Venn diagram, this is divisible by 2, this is divisible by 3, and we have this intersection in the middle, which will be the numbers that are divisible by 6, both 2 and 3. So that means these are the numbers that are divisible by 6. So I will have to subtract that once by doing this. Okay, so that's for 2 numbers. What sounds simple enough. What if it's 3 numbers? Right? It looks like this. Okay, same as before. I can add these in. I can add these single ones in. Okay, I'm gonna zoom in here. So I can add these in first, and then I subtract their these overlapping parts. So I remove this once, I remove this once, and I remove this once, and then there's gonna be a problem, right? So let's go through each section here. This gets added once, and it is removed 0 times. So it's added once and removed 0 times. So this is counted once. That's good. And then this is also the same. So each of these are already calculated once. But this we are doing as it we add this and we add this. So that's adding 2 times. That is why we need to remove this once, which would bring it down to 1. Same for this and this as well. But this middle part right here is going to be our problem. So first, we add 3 of them, right? Because it's overlapped by 3 circles, 3 regions. So it's plus 3. And then we remove 3 times because this overlaps with that as well. This also overlaps and this also overlaps. So we remove 3. So for this middle section here, we need to, instead of removing again, we need to add another one to make this 1. Because we want each region in the Venn diagram to be counted exactly once. So let's say, okay, this is kind of a hard topic for me because I know how to do this already, but it's kind of a hard topic to me for me to explain. So if you are dealing with, let's say you are calculating for regions that are overlapped, that are, okay, if you're taking one value in consideration, then you're gonna add it, right? If you take 2 values into consideration, which means these regions here, then you're going to subtract them. It's 3, then add. And this pattern of adding, subtracting, and adding, this continues on. So 1, 2, 3, 4, this will continue on, okay? I forgot what theory this is called, but it's just this. So okay, I'm just gonna call this real quick. So for x, first I'm going to go through, let's say this is long sum. These will be the how many numbers there are, valid numbers there are less than x. So I will make a bit mask because I noticed coin's length is less than 15. So I can make a mask. I can use a bit mask here. Is equal to okay, 0. No, 0 is going to screw me up. And then if mask is still less than 1 over, I'm going to pass in the length of, okay, this is going to be n. So the mask will determine which values we're taking into consideration. Now I will have another value called product. It's 1, and I'm going to iterate through this map. How do I this goes up there, so I take this, take that. You know what, I'm just going to go 15 because I already know that it's going to be 15 numbers at most. Oh wait, no, it's just going to be n. Oh, I'm done. Okay, so it's going to be n. And if the bit position at that position inside the mask is on, then product will be multiplied by, yeah, I also have to pass this in. Now this is so I'm just going to replace this. Okay, int n equals coin dot size. There we go. Okay, so we have the product, which is, for example, let's go back to the 2 and 3. So what the mask is doing is, let's say I have 2 and 3, okay? And I go through each possible bit of the map. So it's going to give me 0, 1, 1, 0, and 1, 1. And the product over here is going to be 3, 2, and 6. You see what I'm doing? The mask will help me go through every possible subset of all the coins. And then I have to check if the number of bits that are turned on is odd or even. If it is odd like these, then I would just need to add floor of x over p. Okay, so the number of values that are divisible by p is going to be x over p, right? And the odd or even will help me determine if I add this value or I subtract this value. For example, these two will be adding and this is subtract, which is exactly what this is. Okay, so I have this. I also need something called a bit count. Yeah, I'm going to do this. And then if bit count is odd, that means this is 1, then I add it. So sum will be added with, what is it, x over product. Okay, else sum will be minus by that and return sum. Okay, so this is the code. This is the function that will help me count how many valid values how many values you can make with these coins that are less than x. Okay, I can say how many values less or than or equal to x that are divisible by at least one value in coin. Yeah, that's a better way to phrase it. Now I just need to binary search down here, which is our initial plane. R can be, what is the upper bound again? Oh, 5. Okay, so 5 times so 5 E10. Alright, that works. And our answer will be 0 first. No, wait, no, we're finding the maximum, the minimum, so it's going to be 5 E10 as well. So while L is less than R, get the mid, okay, this is just dividing by 2, okay? Don't overthink it. Then if count valid mid coins is less than or equal to k, then I will reduce answer can be mid, and R will be mid minus 1, else L equals wait, hold on. If it's less than k, oh, it's the other way around, okay. So if it's larger than yeah, okay. Then I guess I just return answer. Okay, it's not very hard. Oh wait, hold on. Bit count, yeah. Okay, now it's just bug fixing. Okay, it's running forever. That's not a good. Why is it running forever? Okay, I'm going to print out L and R. I am suspecting that these are not approaching each other. That's why. Yeah, it's stuck here for a very long time. Oh my god. So why is it stuck at 5 and 9? Valid. Yeah, okay. Okay, so it drops and it doesn't drop anymore. I mean, yeah, sure. Is this wrong? L plus R minus L. Oh, I forgot. Did I forget? I don't know if that's the problem, to be honest. Because I don't think that is. The reason here is that, oh wait, what? Oh, so it was the problem. Okay, so case 1 is correct. Wait, why was that wrong? No idea. Because that shouldn't be wrong. But it works. Okay, so case 2 is wrong. it drops down to 21, and then this gets increased. Why? Because the mid is am I missing something? If mask over I, if the ith position of mask is 1, then times that in. Should I floor this just for safety? Because I don't think I should. I mean, I don't think I need to. Hold on. Why am I having yeah, okay, yeah, it doesn't change anything. C++ already floors that by default, so I'm wrong somewhere else. Bit count equals 0. Bit count gets added. 5 and 2. Oh, this is 14. Okay. So I'm trying to find the 7th number. Okay. So if it's counted valid, the amount of valid number is larger than 7, then decrease. But this is not larger than 7. Oh, so this should be equal to, I think. Then the first one, yeah, the first one messes up. Okay, what if I go the other way around? So we know that I know that we want to find the smallest value that has this. So this should have been correct. Why is it wrong? It's larger than k, right? No, it shouldn't be larger than k, because k equals 3. No, it should be this. Okay, so I'm going to print this real quick. X and then count, because I want to see if this is being calculated correctly. So I'm gonna ignore the bigger values. Let's see here. 5. There's one value smaller. Correct. 7. There's 3. That's not right. Mask is 1. Mask is less than 1 over to n. Increment mask. Then go through all of the positions. Wait. 1 over n. So we go through 1. Okay, so 1 over n here. I think it's over counting something. This might solve it or return an error. Oh, what? Okay, this is not helping. Oh yeah. So we know the product of this. Okay, what is wrong? I thought I got it. Okay, I'm gonna add a small test case because I want to test this. Okay, let's say 2 and 3, like our classic example, and it's finding the 5th number. Okay. Okay. Yeah. So I'm gonna list this real quick. So it's going to be 2, 3, 4, no 5, 6, no 7, 8, 9, 10, 12. Yeah. And then 8, there's going to be 5 numbers, that's correct. 7, there's going to be 4 numbers. 4 is 3 numbers. 10 is 1, 2, 3, 4. Yeah. What's the problem? Yeah, for 2 and 3, it runs perfectly. 5 and 2, it also runs perfectly. I think something here is wrong. So let's say there's one number, then I wanna go through that. It's either take that or don't take that. But my product cannot be 0. That's why I need to have at least one number in there. Okay, so this is wrong. You already know this is wrong. 6 is 3. No, 6 should be 4. If bit count is odd, then we add. If bit count is even, then we don't add. So what's wrong here? It's not going to change anything, right? This is kind of frustrating because it could be a very small bug that I'm not seeing here. A very small error. Okay, I'm going to remove this. Product equals product times coins. Bit count adds up. Human enemy. I know this is gonna print a lot, but to be honest, I only need the first line, like this line. So 5, it uses 1. Yeah, 2 uses 1 and 10 uses 2. That's correct. That's also correct. Why is this wrong? So 3 is 1, 6 is 1. Yeah. Oh, wait, no. Oh, wait, I know what's wrong. This is only under the assumption that the coins are prime, but they're not. So what I actually have to do is, oh god. Okay, new plan. It's not entirely wrong. I can keep the code above exactly the same. How should I inclusion exclusion this? Oh, it's just taking the LCM. Okay. GCD of x and y. Oh god, do I still know how to do this? If y equals 0, return x. Yeah, you know, I'm just going to use the built-in function. I don't want to do that right now. If GCD equals -1, then GCD is going to be equal to coins I. Else GCD of coins I and GCD. So I got the greatest common divisor. Now I need the lowest common multiplier. That's going to be product divided by the greatest common divisor. This is going to be LCM and LCM, I think. Okay, let's hope this works. I generally don't know if this works. Oh, server error. It could. Oh, what? Unknown server error? No, I forgot how to do this. Okay, hold on. Int GCD. If y is equal to 0, return x. If x is less than y, and then we swap x and y, and then get GCD of y over x. And y. Okay, that is completely wrong, I think. Okay, hold on, I'm just going to print 5 and 10. It should return 10. First line. Oh yeah. Get GCD. I forgot that I don't have the built-in libraries. I haven't included the library, so I can't really do that. No, stop this. Just run. Okay, did it print 10? Yup, it printed 10. Okay, I still think that's wrong. God. Yeah, it is wrong. Okay. Okay, I'm going to GCD because I genuinely forgot how to do this. Hold on, where is it? I think this is it. No. Yeah, this is it. B equals 0, then return this, or return GCD B, this, equals, oh, it's just that. So if B equals, Y equals 0, then return X, then I return, what? Return Y, X over Y. I'm still not sure this is correct. So it's getting the lowest common factor of these numbers. This should be not 1. That should not be 1. Oh, I think that's the problem. Stop telling me to subscribe to premium. This is your fault. Oh wow, that actually worked. What the hell? Okay, please tell me this is it. I don't want to debug this anymore. I'm just going to submit after this. Oh, 466 test cases in, and I got a wrong one. Sure, use this and print the previous stuff. Let's see this. Okay, GCD is 6, LCM is 6, bit count is 1 because it uses 1, it uses 6. LCM should not be 1. Oh no, it should be 1, okay. GCD is 1, that is 6. And then that's 2, 1, 2, 2 and 6. It gives 6, it uses 2. Should I just throw this to some AI to help me figure this out? No, I don't. Okay, let's go through my logic again. So this is wrong because this only works if all the numbers are prime, but it's not. It's not prime. So what is the problem here? No. Wait, I'm dumb. Oh god, this can still work. So I'm going through these numbers here. Less than or equal to 25. Okay, so I'm going to make another one because I want to remove all of the numbers where y is divisible by x. So I'm going to iterate through coins. Equals 0. Then both valid equals true. In a sense, until proven otherwise. So I minus 1. J is larger than equal to 0. J minus. Then if coins, I should sort this first. Should I? Nah, I don't need to. Okay, so I can just do this as well. What if they're duplicates? Yeah. Begin, end. Okay, so now all of these are unique. All of these are unique. Then another vector. This is going to be our final vector called vector A. So I'm going through B size. So if I equals J, continue. If BI divides BJ equals 0, which means BI is already included. So I valid going to be false, and I'm going to break the loop. Okay. So if no valid, then I dot push back BI, and then instead of coins, I'm going to use A, and this can go back to using product, right? No, it's still LCM. Yeah, that's not how it works, I guess. And it's the wrong answer, 500. Oh god, I'm not debugging that. So I go through b.size. Let's look at discussion. You guys are struggling with test case 522? I'm nowhere near that, I think. Oh, I already passed that. What the hell? Yeah. I don't know what is wrong anymore. Just going to call this RAM now. product is divided by this, I'm going to get the LCM of all of that. Because I know that if I do it like this, there's going to be overcounting, undercounting, and all of that. Okay, let's see solutions then. I want to see how they include and exclude this. Yeah, how do I calculate this? I already go through this. I already go through this. Yeah, what? This is exactly what I did. What? The least common multiple may exceed the integer range. It's already long. Since we can pre-compute the least common multiple every subset, then traverse all subsets during the binary search. Yeah, sure, I already did. I didn't do that yet, but I'm sure. No, I did this. What is wrong? What is wrong? How did you do that? Oh my god, it's also mask. Okay. Current LCM is equal to 1. Alright. Let's look at this. Divided by GCD. Wait, GCD is a built-in function? Like I can just do this. It's good enough. Like I guess current LCM going to be 1. Then what's this? If temporary is less than R divided by coins, what is this guy doing? If mask is, where's R? Coins 0 times K plus 1. Oh yeah, he did say that it could exceed. Yeah, so they can be skipped. Okay, I get where that comes from. Alright, but I'm just going to count them anyways, because why not? What? It's just going to be GCD of... So that's this current LCM divided by GCD, and then I add it back in. So it's this divide and then times the current one. Okay, yeah, sure. That makes sense. Let's see, divided by GCD of coins I. Okay, so based on what they said, I do not need this entire thing. So I can just have coins in GCD of this and current LCM times coins I. Okay. Oh wait, no, that's going to be, yeah. Hold on. Current LCM equals 1, and that. Yeah, I think the problem was just my calculation of LCM was just wrong, which is my bad. But I guess my general idea was correct, at least. I could have done this. This is so much cleaner. So it's not beating much. Okay, so I'm going to let's see here. So length equals this, so I can just pre-compute all of that. Alright, sure. Let's see, LCM, sub LCM, 15. So 15 is going to be around 2 to the power 15, that's 5, 1,000, 2,000, 4,000, 2,000, 20, 2,000, 4,000, 8,000, 16, 30. I'm just going to put it at 40,000. Yeah, and same for subproduct, also pro. And I can move this, copy this, move this down here, like pre-compute this and all that. So bit count, yeah, sure, also why not. Okay, so I have all of this. This is going to go through all of that. So after this, bit count of mass going to be bit count. Sub pro of mass is going to be product, and sub LCM of mass is going to be current LCM. And then I don't need all of this recalculation. I just need bit count of mask sum and sub LCM of mask. Sub LCM of mask. Okay, I think something was not needed. What sub LCM? Yeah, sub product. Huh? Oh, yeah, I don't need sub product. Why did I do that? I just need this. Okay. Error. Sum LCM. Oh, sum. No, stop sending me that. Do your thing. Coins dot size integer this. Oh god, okay, int n equals okay. I think this video is so long. I'm such a dumbass. Okay, submit this. This might perform better because I don't need to recalculate everything. Yeah, I did perform better, but the memory is just ass. So I think just need, let's remember this. So 100,000 is 20 divided by 10, so I just need 30, I think. 25, yeah, sounds good. Submit again. The memory might do better. Yeah, still worth. Okay, never mind. Okay, I passed with some help from the editorial. My idea was right, but I was just a dumbass in one of the steps. Anyways, goodbye guys. This is a good problem, right? This is a good problem for beginner competitive programming. At least it's better than the Stone problems. Alright, I'm out.